Um, okay, I think the live stream is going, so it's good. So what I want to do today, and I mean, I want to take a look at the wonderful Linux memory management, not memory management, but specifically its virtual memory management one more time. And the reason for that, man, really, the reason for that is to make sure that we all understand how it works. Because as I was like going through it again for myself, I understood that maybe most likely I don't understand it fully, or if I do, I still need to want to discuss it one more time. On grade school.
Not in Canvas.
Just grade school.
There's another button.
Got it. Oh, so did on Canvas there is also a submit button? I created the homework in Canvas just so it shows up in your calendars. You don't have to submit there. Sorry, I apologize for that. Any other questions, by the way, about the homework?
The figure.
The figures, yeah. So people were asking how to submit the figures in Markdown, and I don't have a good answer. So do you guys know the best?
Yeah, then upload the images on like some global like Google Drive or like you have something like this and there's a copy.
Right. So that was my only solution as well, but maybe there's.
Marmite chart code.
That's a good one as well. Yeah. That's totally fine. So I like ASCII drawings as well. And whatever works. But okay, so sorry, like back to the memory management. What I wanted to say is that it's very important to understand how it works because I mean, after designing a couple of the operating systems with my students like Zahan, Gary, Brando, who is not here, you always run into those problems. Like really, you're solving the same problem over and over. So unless you understand how it works in Linux, and Linux makes a decent amount of good choices, you don't even know like how to improve on that. So I just wanted to talk about it one more time. So because I don't think I did a very good job explaining how like stuff works last time. So just wanted to make sure that you're there. So remember that Linux tracks every physical. Maybe I should make sure that I have more space at the bottom. It has this array, which they call a page info array. And this page info array tracks the state of every physical page in the system. And as we'll keep talking, I will be asking questions about it. So this is called a page info, right? And I'm pretty sure you guys know probably even more than I do because you were working on a homework and stuff like that, right? So, okay, cool. So we have page info. We also have a virtual memory of a process, right? So for every process, so let's imagine we have a process like that. I'll draw a box for process one, right? It has a virtual address space. And for each of the allocated region of the address space, Linux uses something what is called a virtual memory area, right? Roughly speaking, just to start with, it contains the start address and the end address of this region, right? And if we have a second virtual memory address, it will also have a start and the end region. So this is start, this is end, right? And the process itself is a task data structure, and the task data structure points to something what they call a memory descriptor, or MM. Not sure. I was calling it memory map, but maybe I'm wrong. So they say it's a memory descriptor officially. And this MM in the past maintained those VMAs on both a linked list, right? And so on, like imagine you have multiple here. On a linked list and in a red-black tree. And as I was going through like what other people are saying about it, like I forgot the exact names of the fields. This was mapping, I think, or what? Or mmap, and the red black tree is essentially, let's draw it like this. It's a red black tree, which essentially, like leaves of this will point to memory regions as well, right? Agree? So I think one would imagine that I kind of explained why linked list is not enough, because if you have a very large number of those virtual memory areas, obviously searching from a gap for a gap would require you a linear scan, which is obviously prohibitive. But and you say an obvious answer is a red black tree or some other tree, like for example, actually, if I understand correctly, even the red black tree is retired as of today, but I'm not 100% sure, but you guys know, right? But the point here is that, like, the question one may ask, which I do have an answer for, is why do they maintain a linked list as well? And apparently, in the past, the logic was that a large number of VMAs was typical for some only subset of processes. So they were trying to balance processes which are reasonably tiny, like LS, for example, right? Which only has just a handful of VMAs, let's say 10. And the large processes like databases, which have hundreds of those VMAs, because they memory map a bunch of like files which contain tables, they bypass the file systems, they might even do something like what is called a direct mapping, which will bypass the buffer cache but will ensure like direct writes to memory, right? And so if I understand correctly, and that's my guess, is that they were saying that sometimes traversing a linked list, just because of how the constants work, like ON versus O log n for a tree, at some point, you know, ON is still faster because the constants of traversing a linked list are so low that it's just faster than going through the red black tree. If I understand correctly, that was the logic, but I'm not 100% sure. And if I understand correctly, today they retired the linked list and only left the red black tree, right? Agree? Okay, cool. And don't forget that VMAs track the address space of a process, right? And obviously, like memory allocators use this trick which says, okay, that a physical memory of a kernel is mapped with a Swift. So we can come to it again, but probably you understand it reasonably well. So essentially, it allows you. It's kind of unrelated to this drawing, but if you have an object which you allocated from kalloc, right, from a kernel memory allocator, and you want to do a K3 on it, so essentially K3 of the same object, in order to understand which cache to use, right, they do a virtual to physical conversion, like essentially shifting it by a certain specific offset, and it essentially leads you to a page entry, and a page entry will contain a pointer to either a slab or a cache. I don't remember exactly. Someone remembers cache or slab? Cache. Because in the end you have to like, but then you still need to resolve into a slab, right? Because you need to like add on a linked list of a slab, right? So then, okay, this pointer, let's mark it. Since I haven't looked at it for a couple of days, we can question it, right? So, or if it's, if it came from a body, right? Or remember, kalloc can allocate a very large object from a body, then this pointer will point to something what today is called a folio, right? But and I figured how it was called in the past, some combined or grouped object. It's all folio, right? Right, but in the old days, it was like, imagine you allocated as a group of 2 pages, then this one will be pointing to like the start page, right? And then you can which seems wrong already, because you say, look, what is it I'm doing if I'm free, like in the middle of it? right? So it shouldn't be the case. So you should, I think there's like a bunch of like unlikely paths, but essentially points to itself, and then you can check whether the body, which is like, I mean, the page which is the body for this one is free or not, right? And if you can, if it's the case, you can merge them, right? Do you still remember this? Okay, but my primary story today is not about this. It's just like a reminder, and you will write this story and then we will publish it, right? But I want this to be kind of written and understood as well. With, even if I make a mistake today with those 2 pointers, I would like you to explain them to me. And again, as I said, I will judge, I will grade on participation, so you can submit anything, but I just hope that, there will be a couple of people, majority of the class will try to explain it well, and that's where we can publish. But what I wanted to go to is that, remember yesterday, I kind of was using, not yesterday, Monday, I was using this abstraction of an address space. And it's kind of like even counterintuitive, because typically you think of an address space as of something what is like related to memory. But clearly this address space was sitting in front of a file, right? And the idea, the origin for the naming is that they say, they kind of say that like a VMA can point to something, and this something can be a file, or maybe a disk, or even maybe just an anonymous memory. And the address space is to convert from the addresses within the VMA, which are virtual addresses, into kind of address space of that object which sits here. So if it's a file, for example, they will convert like into a page or into like into a page which contains file data. So that's probably the origin of the name, right? But what I wanted to explain, I wanted to make sure that we understand how it works one more time. So what's important to understand here, that those VMAs here, which I'm drawing here, there are really just 2 cases, or 2 major cases, and I think it's just 2. And those cases are, it's either anonymous, meaning that it's just memory, like heap or a stack or something, or it's mapped by a file. And these 2 are handled differently, right? But I just wanted to make sure that we understand how each case is handled, right? So an anonymous can also be private, not shared with other processes, and shared, which can be a result of a copy on write, or even just establishing the region of shared memory between 2 processes, for example, right? So let's take a look at these 2 and just make sure that we understand what's going on. So first, anonymous memory. So this case, in case when it's anonymous memory, what we need to handle, we again need to handle the motivation for this architecture is to be able to support these 2 operations, which I was discussing before. So one is a kind of demand paging. And another is like memory reclamation or swapping out or swap out. So kind of like swap in and swap out, right? And so, as I was saying before, when you even allocate a new VMA with, let's say, a region of anonymous memories and not backed by a file, those pages are not originally allocated in most cases. Maybe there is a case to force Linux to make sure that those pages are allocated eagerly, but typically they're only allocated when there is a page fault. So when you hit a page fault, right, what happens is that you have your current struct, task struct, will have a memory map or memory descriptor. Then you can take the virtual address as an input, walk the red black tree, right? And land on a VMA. If you don't land on the VMA, it means that you're doing something funky in most cases, right? Because it means that you're trying to access memory which was never allocated, right? In most cases, it's a page fault. But it might not, not a page fault, it's a seg fault, right? It means that you just have a stray pointer, you're trying to access memory, which is somewhere like in some weird region. However, at least in one case where you're trying to grow the stack by one extra page, and for example, you're hitting this page, and this VMA will have some kind of a growable flag. That's a legal operation, right? And you say, look, your like originally the stack was that big, and now you're trying to like add an extra page, and that's fine. So we will allocate this page and be happy, right? But for example, in a normal case, when you hit on a VMA, so this is like an exit from this red black tree, you say, look, I clearly need to allocate a page. And you do allocate a page, and so this guy will have a pointer to a page table as well, right? Page table directory, right? So I only draw 2 layers, but then 64 machine will be 4 or 5 layers, right? And then you just get a page from a memory allocator, and essentially just add the mapping, right? So I wanted to say with them like the page which corresponds to this entry in the array will be added to the mapping, right? However, what also happens here is that remember that in the end, we want to handle something what is called a copy and write. And we will create something what a data structure which is called a non-VMA. And the reason is this data structure will be keeping track of all VMAs which are sharing this region, right? And that's later on to ensure that we understand how the copy and write works. Already a little unusual, but essentially, like if in case of a file, remember there will be this Redux stream, which I will just put in the board in a second. Linux, in this case, Linux doesn't really maintain any metadata about the pages associated with this VMA. So the list of pages is not there, if I understand correctly. And the only thing which they do is they really just maintain this information in the page table. So if you want to see which physical page corresponds to a specific page in the VMA, you really have to walk the page table and get it, right? So typically you don't have to walk, because if it's a page fault, you already have the hardware. You have a faulty address, right? So you just know that it belongs to a VMA, and then you say, look, it's a legal VMA, so there might be like a, okay, let's get to a copy and write when you have to upgrade from read only to read write. But let me just cover the case when it's backed up by a file, right? So let me stop here for a second. Is my story here still makes sense up until now? So we understand how it works. Again, our main goal is to support like managing virtual address space of a process. And the answer here is VMAs essentially just it's a list which manages like a list of sparsely allocated regions plus a red black tree, right? And we really want to support like demand allocation, demand paging, and swapping out, right? Okay, cool. So when the VMA is let's say sort of drawable here, I will say is backed up by a file, then instead of like having this unknown VMA, what we put here is that I have it on a slide here. So let me just refresh my memory. Sorry. So we have a pointer to a file, and a file will have a pointer to an inode. And an inode will have a pointer to this address space, which I was describing here in a second, right? And the reason for this indirection, the fact that instead of like going directly to an inode, I mean, inode, obviously, you need an inode. Okay, first of all, do we remember okay, why do you think we need an inode here to begin with? They're like 3 data structure, they have specific meaning. inode, role of the inode. Remember, it's backed by a file, so it's at some point you have to go to disk and either read or write from disk, right? And why do we need an inode? Remember, we talked about it last time a little. That inodes do what? Correct. So inode will provide you a mapping from a file offset to a block. And it's a job of a file system. So inode itself, like in memory, doesn't have this information, but by knowing the inode number, you can communicate with the file system, and it will say, you remember this direct entries and like indirect entries, which represent like essentially it allows you, it kind of maintains, not in memory, but on disk, it maintains a tree, which allows you to resolve from a file offset to a block number. So we'll draw it as a tree. And this tree is typically, I mean, it might not be a tree, but typically it's a tree. Into a block number. Right? Agree with this? So for that, we need an inode. Without an inode, we don't know how to read stuff from disk, right? Why do we need files? Well, a file descriptor, yeah, so okay. A file descriptor is roughly just there's a file descriptor table. Typically, when we say a file descriptor, we say like number 2. And this number 2 is an entry in the file descriptor array. And the pointer from here will be a pointer to a file data structure. And this is this is the file data structure. So what does this data structure keep? Which information? Do we remember? Not exactly. Even when you open a file, it will keep something like an offset, right? For this specific file descriptor. Because the file can be opened multiple times, right? And in this example, for example, these 3 VMAs are backed by the same file, which is represented by the same inode with this, right, over it. But they need like mapping even like different parts of the same file. And this offset will tell you, okay, like I'm mapping the beginning of the file, I'm mapping the middle of the file, and I'm mapping the end of the file. And just this VMA starting from this offset within the file, right? So VMAs are different and they're contiguous, right? So essentially when you have a page fault here, plus the offset, you will know which part of the file you're mapping, right? And it's similar in a file system when you do read and write, even if you open the same file twice, like same inode twice, it will be 2 different file data structures, right? And they will have different offsets, and you can read and write from different parts, right? So, okay, we got this idea, right? And then, say again?
You just say they read and write, but at the same time, is it possible?
Yeah, it's possible. Remember, the buffer cache will serialize the accesses, because when you do a write, you will need to acquire a buffer from a buffer cache. And at this point, because when you will be doing a write system call, it will be really a system call which take a file descriptor, a buffer, and a len, right? And if you do it twice, like 2 different writes, right? At some point, under the hood, this write will be processed by a file system. There will be a transaction, like a journaling thing. But at some point, you will say, look, I'm copying this buffer from user level into like the buffers which represents like things from a page cache, right, or a buffer cache, right? And at this point, like one of them might win, and they also might. I don't know what these consistency guarantees will be, so because maybe they can actually overlap in some non-serializable manner that I don't know. Yeah, probably. So, but in general, operating systems support it, right? There is no like restriction that you cannot open something multiple times, right? Okay, we got this, right? So file inode address space. Files because multiple processes can open the same or map the same file at different locations, right? File is the same file is represented by an inode. Inode is an actual thing on this, right? So it's a file of this. It's an unnamed file because the name is given by the directory, right? So inode can have multiple names if it's linked from multiple parts of the file system, right? Okay, and so in this case, remember there was another interesting data structure here, which was what? Just this data structure was a registry. And why did we need this one? It's on the, it's here on a slide. So why? You can tell me. To locate a page in a buffer cache, which represents a specific position in a file, right? It might not be there, so then it's not in the registry, then we have to locate a page and insert it into a registry, right? But for example, if we're servicing a fold, which means that we're servicing the fold, we made it like we went through this red black tree, figured out that okay, this is this VMA. This VMA is backed by a file because there is this field which is not zero. Then we go to an inode and we go to an address space. We do like from here we pick up like an offset. From here we will pick up like offset plus whatever the delta in which you faulting. Then we go into the address space and we say, look, maybe this is mapped by a different address, by a different process, and there will be a page in a buffer cache. It might not be there, and then we'll allocate it, right? And we'll bring it into a cache from this. And we will reach from this by using this file offset and like whatever the file system will do the read. It's like hidden from us, but we will use an inode to read it, right? Okay, so this is cool. Now we understand that, like again, what I wanted to highlight that there are two cases: either anonymous VMA not backed by a file, or something what is backed by a file, right? And here on this diagram, we see how the sharing between the processes happens, right? So if you have multiple VMAs which map the same file, that's the data structure, right? So essentially, your VMA will lead you to a file will lead you to an inode will lead you to an address space. You will search in the registry, and if you're lucky, you find a page. If it's there, you just will update your like the page table mapping. If not, you have to allocate a page into it, right? The question is like, what happens to those anonymous VMAs when you do a fork, right? So remember in x86, when we were doing a fork, and essentially, like, let me just connect this one. In x86, so when you forked, like imagine you forking one process 2 from process 1, you would just literally walk the page table and copy every entry, right? That's how x86 was doing before. Agree with this? And it worked, but it of course it's a huge overhead because maybe you're not going to even, maybe it's a very fast fork, which will immediately do the exec, destroying the old address space. So that there is no reason to even copy the address space because it will be destroyed, right? It might execute like 2 instructions in the child, and the child will hit a couple of pages which contain the code to do the exec, right? Agree with that? And so obviously those guys immediately optimize this case, saying that instead of like copying the address space, we're going to copy the VMAs. So those will be copied. And we're going to copy the page table, right? So essentially, there will be a new page table created for this new process. And this unknown VMA will be created for reverse mapping, making sure that we can like later on understand if we hit a page on a page fault, we will know all the VMAs which are mapping this page, right? And I will explain why in a second. So, okay, so imagine And I forgot, like, I have a slide for this. Let me just quickly. I don't have it here, but I had it last time. This one. Buffer cache, no, it was in the lecture 2. Lecture 1, lecture 2, this one, right? So it will look like this, right? So we have this, we essentially, man, this is how PowerPoint just ruined my slides, but that's okay, we'll still do it. So essentially, like the page table is copied, right? So it's here. So in each process will have its own memory descriptor. We'll have this PGD pointer to 2 different page tables, right? But these leave entries will point you to will lead to the same page here, right? Agree with this? And this page will be marked as read-only, and they will also use an unused bit, unless the architecture supports it, and typically they don't. They will use one of the unused bits to remember that this page is actually copy and write, which is a little unusual, but if I understand correctly, that's what they do, right? And later on, when you hit a page fault, so for example, in one process, you walk through the red black tree, land on this VMA, right? You essentially say, okay, what's going on? Like I'm trying to maybe write into this page and it's a read-only. So you gonna walk the page table, right? Because there is no information about the list of pages on this VMA, right? So you really have to walk the page table. You will figure out the copy and write bit here, right? And you say, look, at this point, I will actually allocate a new page and I will mark it as like, I will allocate a new page. This pointer will be pointing to this new page and this will be writable, right? And the reason you need this reverse mapping to essentially say, okay, what about other VMAs? And I don't really know how Linux does it. So, but you can imagine that it says, okay, everyone else still like stays the same unmodified, right? So, and then you're just fine. Or maybe you want to know who else is mapping, probably it's not needed. And just essentially, if it's the last copy and write, then you can just switch it back to the writable. But probably they don't do it, right? But that's essentially the logic. So you don't need any other data structure. So you go from a page fault, you read this copy and write flag, and you immediately you allocate a page and patch your page table, right? So it seems to work this way, right? Any questions about it? Good.
You said we need to check the last copy on the page.
But that maybe I made it up. Forget about it. That was
not enough because every page has its copy on the page. We don't need to check whether the series of pages. Every page has a
correct. Yeah.
It's enough.
It's just that
we don't care about whether all of them or some.
It feels intuitively that there is some additional trickery which I don't fully understand in like implementing copy and write, because like you need to, so maybe we can spend even more time on this, because you know, the children of children can start forking, and the question is, what happens to this? Are they staying within the same VMA and on VMA? Probably yes. It's just fine. But what happens if you fork a couple of times, this guy again forks, this one already has a page in a writable condition, for example, like this one is writable because it already wrote in there. This one still stays read-only. At this point, do you have to share a page with this guy and turn this into read-only, or you can just pick up a page from someone else, which is already read-only, kind of saving the page, right? Do you understand this trick?
Yeah, I mean, the parent itself to maintain the writable, but the children will just set to read only.
I mean, I think there are some corner cases which are which are non-trivial. So I don't know what Linux is doing. We can take a look because even if you're forking and your page is also already writable,
Yeah.
there might be a chance of finding this page in a read-only state because this guy never wrote into it, right? And maybe you can share a page with this guy, but it requires like a lot of page table traversal, and I'm not sure that it's worth doing at this point. But again, it's
Do you have a reverse mapping value into traversal?
no, okay. That's another thing. So remember that this unknown VMA, this is how reverse mapping is implemented for anonymous memory, right? So it's not the interval tree. Interval tree is only used for files. For this is specifically this diagram, which is here on the screen. It's implementation of a reverse mapping for anonymous regions, right? And so you're right. So maybe the logic here that what the Linux will do, it will actually, when on copy and write, they essentially say, look, this page is no longer, like, since we created a writable page, it's no longer shared between them. And so we will actually create a new non-VMA region, like in a child or a parent, and this VMA will be moved here, and this link, there will be no connection between these two anymore, right? That's one possible strategy. Like maybe I lost you here, so maybe I can spend more time understanding how Linux does it and come back and explain this, but because copy and write is a little tricky. But okay. Hold on. So let me. Okay, did we follow how it all works? So again, reverse mapping will be needed. I'll come back to it in a second. So it will be needed to understand, given a page which we identify as a candidate for swap out or reclamation, we need to understand, like, we need to find all the page table entries, those guys, which map the page, to make sure that we can change them to like not present and then look them up in a swap partition, right? But I think actually what I wanted to explain is here. So what I wanted to highlight is that if like again, a couple of things to highlight. There are two main flavors of VMAs, either backed by a file or anonymous, right? And they kind of split the world in two. So you handle them differently, right? For VMAs, the only information about how the page is mapped, which physical page is mapped by which virtual address is only maintained in the page table. And you have to walk the page table. For a file, it's maintained here in the Redux tree, which, like, knowing the address, you're converting from like file address to a page, you will land on a page in a page cache, right? I have, however, one question unresolved. So for myself, which I don't know the answer to. So how come? So it seems that the pages which are mapped by anonymous regions are never in a page cache. It seems to me, but I don't know for sure. I don't know how to confirm it, because there is no way, like, essentially in Linux, the page cache is associated with individual address spaces, right? And there is no association between this unknown VMA to an address space. So one would logically assume that you can maybe insert some kind of Redux tree here, but then probably it just doesn't make sense to do it, right? The what?
Human page, when say the one VMA has anonymous paging, so it wants to write something, so it needs to be to the actual page, right? But that it has to be collected from a memory.
Right. So it doesn't come from a file, so it's just allocated from a. But the question is, right, so there's probably not a case in which you say that, like, the same page might already be in memory Because if you do copy and write and capture it with this mechanism of linked VMAs, and it's anonymous VMA and linked VMAs, and you say, look, I will mark them as read-only and copy and write, and then later when someone writes into this, since anon VMA is used for reverse mapping, I think they will split them, making one page writable and one page stays probably read-only until it's get written. But at this point, since this will be two different pages, right? So this one points to page kind of 1, and this one will be pointing to page 2. This is writable, this is readable, right? So at this point, probably the split happens, so because otherwise that will be answering the question that this page is still mapped by. No, yeah, it looks like the split has to happen.
This is the data.
Say this again. What?
What is this? It's like delaying the actual writing.
Hold on, maybe.
Yeah,
Like maybe ask a question different because I don't understand how to answer, or I don't understand what you're trying to ask.
so how is it handled? I mean, that VMS that are not supported by any type.
Right.
So say so one VMA modifies or something like something. So how it should be reflected in the physical page?
Like it looks like that. Are you talking about the copy and write scenario when one process forks, or are you talking about something else?
Yeah, like say the process for another process.
Yeah. So then there will be two address spaces, right? I will draw them here. There will be two address spaces with two identical VMAs. VMAs will be created for the parent and a child. The page tables will be also created for the parent and a child. I will draw it like this. And both of these will be pointing to the same physical page, but with a read-only permission and some kind of a copy and write flag, so we can detect later that what to do when the page hold happens, right? And these two VMAs will be placed on the linked list with a known VMA, right? And a known VMA will keep track of, like, if you ask a question like who maps this page, because maybe you want to take it down into a small, the page itself, not the page physical page, but the page in a page info array will, one of these fields, which can change, remember this is the pointer, I think it's called mapping, which changes the meaning depending on whether the page is associated with a file or just anonymous VMA. It will be pointing back to this anon VMA, and then you walk the list and you say, look, I understand that these two VMAs are mapping this page. Each VMA has a pointer to MM of a process, right? And MM will have a pointer to a page table, right? So this VMA will also have a pointer to a different MM, and this one will have a pointer to this page table, right? Right, and this way you can go from a page, from a physical address to all the page tables which map the page, and you can, like, for example, change it to not present, right? But when I believe what happens when there is a write, when a write comes, all right, on either side of this, all right, then I think at this point, this VMA is removed from this anon VMA, and like maybe a new anon VMA is created for this process. And it will be just on this list because we will allocate a new page and we'll patch this mapping to point to this page, right? And it will be in a writable state. I'm guessing that this one will still stay in a read-only state. And only when you later write, they will probably re-upgrade it to a writable, but without doing anything, leaving from the same, just removing this flag and changing this to writable. Here we remove the copy and write flag, right? Just close it over, right? But it seems that it can work this way, right? Okay, so, okay, this is, we now know how to handle page faults, like how to go for both anonymous and pages backed up by a buffer cache, right? Okay, let me just go to my slide deck and see what else I wanted to say. Any questions or anything? Again, my reason was to make sure that we again understand how it works and talk through it one more time. Let me just find my slide deck here. That's not the slide deck, this one. Okay, so we have this. Then like radix tree, I was explaining the radix tree. What I wanted to highlight here is these sizes, right? So the height, if the tree is like the radix here has 64 entries, right? And so if it's height 1, like here, if it's height 1, then you can cover a file of up to 256 kilobytes. If the file is growing beyond, you will upgrade to 2 levels of radix tree. And the upgrade is kind of relatively easy because this part of the tree is exactly the same. You're just kind of adding a parent on top, right? And adding this other half, right? And immediately you cover a file up to 16 megabytes. And then height 3 is 1 gigabyte, height 4, 64 gigabytes, and 5 is 4 terabytes. So the tree is reasonably shallow, right? Just wanted to make sure that we understand this, right? So this is this radix tree, which is here on the board. By the way, I will obviously ask to write this story as a homework, just to make sure that again we, I don't know, like take a picture if you need. Okay, now how do we handle dirty pages? I just wanted to make sure that we understand as well. So, like as I was saying last time, if you write something like here in a page, which is backed by a file, which is located in a buffer cache, the write doesn't, yeah, but, and I can take a picture, but you do, for someone. So writes will be delayed, right? Because they're gonna stay in the buffer cache, hoping that there will be additional writes coming into this page as well, right? So that's kind of like it's kind of not surprising. And what the entire thing will be, this engine will be tuned to track which pages are dirty and how to identify them, right? So let me so essentially what Linux has instead, like the trade-off here is that obviously, like since we saving performance on not writing back immediately, but suddenly the system crashes, like, you know, the data which is still sitting in a buffer cache will disappear forever. And maybe you said, okay, I sold an airline ticket and I remembered it here, but then you crashed, right? And there were like different approaches in the past, and some people said, whatever, like we'll implement some kind of additional power source to make sure that you can flush those caches in case of like catastrophic power failure. But you can actually crash not due to power, but I don't know, like something under like attack, and you, or a bug in a kernel which just halts the system and you cannot sync, right? And so, which means that periodically there's a set of system calls which is not present in actually 6, which maybe it was actually, but which allows you to force the sync of the buffer cache down to the file system, right? And there is a collection of those, right? The sync itself just flushes everything what is dirty to disk. Fsync of a specific file descriptor will flush only the dirty buffers associated with a specific file, and including changes to the inode. Because if you have an inode, remember, maybe it was growing, then on disk, in order to allocate additional disk blocks, you need to flush those as well. And there is a middle ground in between them, fdatasync, meaning that you only flush the dirty pages, but don't bother about flushing the inode, which is a little unusual, but they have it. So, but for example, if you have a very large file which is already allocated, and maybe you already somehow know that, you know, inode will not change. So maybe it will save you a little, but I honestly don't really know when this can happen, right? Okay, so we have this picture. Now the question is, how can we track dirty pages? Where will we track? Because, you know, we did writes in one process into this VMA. Remember, I had multiple processes, and maybe the same file, the same inode was opened through a different file by a different process, right? And there was a write here. So, and maybe they're overlapping, like touch the same entries in this in a page cache, but maybe they're not, right? So how would you implement tracking of dirty pages in a buffer cache?
Finally, this picture something like this. Because
Kind of, but they track. Well, you're right. So you say, look, I can maybe mark the file is dirty and maintain a list of all dirty files in the system, and then walk through this list and keep flashing. But you probably need more information, because what if you just wrote one page like this one, right? And then flashing the entire file doesn't make sense, because there is a ton of maybe pages allocated in the buffer cache, and you only need to flash one page. So you really have to kind of track everything top to bottom. So you will mark a page dirty, and you will do it here in a Redis tree, because the page itself, there is no space to mark the page dirty, right? The connection is from the Redis tree into the page. So you will mark the leaf of the Redis tree, and in order to identify this leaf, you will mark all the parents of the Redis tree, right? Because you will know that they got it. So I will descend into this subtree and flash those pages. If there is like another leaf here, but it's unmarked, you check it. It's unmarked, you never descend. And then you mark an inode, and it seems that this is sufficient. So I don't think you need to mark files, because even if you open multiple files, this information about the inode will be remembered here. And you will maintain a list of dirty inodes, right? And this list is associated with something, what is called the superblock. So here, each file system will have a data structure, which is called a superblock. So this is like a root, this is my home, this is my user. And you will mark that there will be an inode on a list of inodes, or dirty list here as well, that this one is dirty. And then you descend into the Redis tree and you know what to flash, right? And so the Linux does it essentially. At this point, the algorithm is reasonably trivial. You say, for each S in the superblock list, if S is dirty, then try to write back S, which means that for each inode in the inode list, if inode is dirty, then write it back, and you descend into the Redis tree and traverse it, saying, okay, like let's start from the root and only descend into the children which are dirty, right? And then you flash everything, right? And it might not always work, because sometimes some of those pages might be locked, meaning that someone is actually writing into them. And so you cannot flash them because you're in the middle of something. So what Linux does, they implement this in general, they try to avoid asking you to do an explicit flash, right? So somehow it works, right? So it's very rare when we lose data, right? But what happens is that Linux starts a bunch of threads, which are called PD flash, page what? Page D, what is it? Daemon? Or page, I don't know what D stands for. But those threads, and depending on the configuration, they will be scanning this list of inodes and list of superblocks, trying to flash stuff, right? And they have a specific like quota. They say they have a every time they like periodically they get a goal of flashing so many pages to this, and typically it's like cleaning only 10% of dirty pages in a buffer cache, right? So, and also maintaining other metrics like do not let the page stay dirty for longer than some amount of time, say 30 seconds, which also makes sense, right? But there is no like, I think if you really want to flush everything with sync, then we'll be waiting for those pages to get locked and stuff like that. So they try to avoid it, right? So they run those PD flush. So if you do like a PS on your Linux system, you will see a bunch of those. I think it's still called PD flush, or it could have renamed it to something else, but I think it's still the same. So you just know that this is how it works, right? So it flushes stuff in the background. What else would I will? So 30 seconds, quarter, and again, like how do we know? Remember, like my whole story today was about to make sure that we understand how to resolve the errors, right? So since we know the address, remember that this Redis tree, it tracks the pages which represents parts of the file. So they don't track the block addresses or anything like that. These are just cached pages, right? But when descending the Redis tree, you know the address within the file, right? And from there, you can essentially figure out the block address. Am I right? Or yeah, because the Redis tree tracks, like again, if you forgot about it, the Redis tree tracks the essentially the logical locations of a file. So essentially, the input here, it's not really clear, but like it's an address it's an address in terms of pages within the file, essentially. And then you can convert into blocks. I will explain it in a second, right? But this is clear, right? So this is how you get the address. What I wanted to say. Okay, so yeah, inode, remember I was saying that inode is critical to track from the file address and file offset into the block node. And so which means that the address space should have a backward pointer to an inode. And it does, it's just that I don't remember how. Do you remember how? You can do a circle, but no, probably you just remember it somehow, right? Do you agree with this? So because this is to write a file. So you probably just remember the inode on the way when you were descending to that. That's the inode you're going to be dealing with, then you're going to write into it. Okay, but there was additional interesting bit here, which I skipped last time. So remember that still older disks, like spinning disks, their block sizes are 512 bytes. So today, you often, if you buy NVMe, you often actually configure them with something like a 4K block, right? But to support those old devices, back in the days, it was just the thing. Typically, if you have a 4K page, which you allocate here to track multiple blocks, you will end up with what? With 8 blocks per page, right? And there is this mismatch. So essentially, imagine the page is found dirty. But what if you wrote only one block? How do you, I mean, you can either write all 8 blocks. And again, today probably is not as prohibitive, especially, of course, if there is a strict match, one block, one page, this problem doesn't exist. But if you have a smaller block, how can you solve it? So you apparently have to track the dirty thing at the level of a block, not at the level of a page, right? So and Linux has this support. So I talked a little bit about it, but actually I probably misunderstood why we need this thing. But essentially, because I was thinking that those buffer heads, I thought that they only will be used for implementing the legacy buffer cache, but they are also keeping track of dirty blocks. So what happens here is that if you're going through a regular file read and write and writing an actual block, then Linux maintains those buffer heads, which kind of like, okay, you split the page into individual buffer heads, and they actually mark only one of them as dirty. And essentially a page descriptor will have a pointer to the beginning of this buffer head list. And then you quickly scan which ones are dirty, and maybe it's like a couple of them. And then you only write those back to this, right? And it only works for the like a regular read-write interface, because if it's a memory mapped file, the only way you can detect dirty is through a page fault, because you say, or through a page table, if it's already written. Probably they do a page fault actually. They probably map it read only, and then you can theoretically detect it through a dirty bit in a page table, but I believe that Linux will ask you to do a page fault. And then of course, while you unmap, you convert a page once from a read-only to writable, and then because page tables are just too expensive to handle, and then you will just say, okay, look, despite the fact that maybe I wrote just a couple of bytes into the page, you will mark the whole page and the whole list on the buffer, and it's dirty, and then you have to bite the cost and like flush everything to this. So, but I just wanted to make sure that we also understand that there is this piece of infrastructure which tries to handle dirty at the level of individual blocks. So in many ways, I mean, and I think I think I covered almost everything what I wanted, but again, if you try to design something equivalent in terms of functionality, you will probably end up with similar data structures. My goal again today was to emphasize one more time that, you know, you have, okay, I erased here. You have two kinds of memory, anonymous and backed by a file. And you really want to support these two operations, which were here on board, demand paging and swapping out, right? I still didn't cover swap out, so maybe I should come back one more time. Not spend the entire hour, but just quickly explain how it works. I don't know myself yet, so I can explain today. But at least we know how like the buffer cache works. And it's okay. So the third operation, which is important, is the buffer cache, right? And now we know how it works. And we also know to like with 90% confidence how copy and write works, right? So essentially, none of these data structures kind of like looks artificial to me. So in many ways, I believe that this design kind of makes sense. So I could not do it better unless maybe there is some specific problem and it gets solved from one version of the kernel to another, right? And maybe it's already different slightly, but at a high level, this seems like a decent approach. If I ask you tomorrow, or someone asks you like, you know, you have x86, can you design a full-featured memory subsystem which supports copy and write and buffer cache? Then you probably should arrive to something like this. And my hope is that I mean, it's hard for me, so I didn't look at it for like the last 5 years, so that's why I don't remember. But now I looked again, and I will try to remember how it works, but at least it will not be absolutely new to you, and you can come up with similar data structures and make this design. So that was my thing, right? So what else? I think this is more or less. Yeah, that's all I have for this. Okay, we have 10 more minutes. Any other questions? Okay, let's think about it. Maybe I didn't cover one of the process, one of the page faults or anything or something like this. Remember, I had two questions here. Why? What was this? Whether this pointer is a pointer to a cache or to a slab, and whether when is that pointer from a page, from this folio pages, and point. Supposedly, every time you do K3, you should be arriving to the head of the folio. I don't know when you may not do it. I have to also double check how the anon VMA split works in copy and write. Split. And what else? And I also did not explain. I did not explain swapping. And swapping means that specific question which I have in mind, which as I was trying to understand how everything works, my question is the following. So you imagine you identify this page as a candidate for swap out. Cool, you use this reverse mapping, you mark the page table entries or this, for example, to say, look, it's not present, so next time, and you marked all of them because you went through all anonymous, you marked through all VMAs in an anonymous VMA, you know what page table entries map the page, you unmap it from all of it. And at this point, you say, look, I take the page to this page goes back to a free pool, back to body. At this point, imagine immediately or like later hit the page fault. You went into the VMA. At this point, you probably, and this is what is missing. The question is like, you have to remember the address of this specific page that it's in swap device. And so there must be some kind of translation between either a physical page address or a virtual page address to a swap. And that thing is missing from this diagram. So I don't know how it works right now, but I will try to clear it out, figure it out for the next week. And then we will probably, at this point, I think we can say that we're done with the virtual memory management. I don't think anything else is left unless you raise some additional questions. So good, anything?
The anonymous pages and the file pages are separate in their list. And then no.
Like when you create a VMA, you already know whether it will be an anonymous region or a region backed by a file.
Yeah.
I don't think there is a way to convert. Maybe there is, but then it's almost like creating.
Yeah, they will classify the LRR list will separate the file.
Oh, so you mentioned to me today that you know that list recently used lists will separate the two.
Yeah.
I don't know this. So
Yeah, separate. They will separate the file anonymous. Also, a special list is not reclaimable. It's kind of like core kernel pages.
Right.
So there are as I know, there are 5 lists: 2 for anonymous, 2 for files. And why 2? One is they call active list, another one is the inactive list.
Yeah.
Yeah.
I vaguely know it, but I don't know how it works. So yeah, I should probably come back and explain it, and then you will correct me if I'm wrong.
Yeah,
Mhm.
when they do the reclaim, they will scan the tail of the active list, and if it is not so active, they will move to inactive list. And in the inactive list, they will scan the tail. If it is
They will scan what?
the tail of the list.
Tail.
Yeah, and in the inactive list, if it is still inactive, it could be active again and it will stay.
Or it's like a second chance.
promotion.
Yeah.
Promotion or stay or depromote.
Yeah, there was
but
this,
when
yeah,
it-
second chance policy or
Yeah,
something
yeah,
like
yeah.
that.
But nowadays they change a lot of engineering parameters inside.
And
Very complex. Not to say 2chainz. 2chainz is the very naive, and then later they improve. Very complex logic now.
So how do they keep track of nmaps that overlap with this? So you nmap a big region, you nmap a story
you mean VMAs?
overlap.
Do they even overlap?
Yeah,
They can?
there is like a typical way to roll like a whole region to serve it, and we have and that's target is going.
They kind of change the protection bits, right?
No, you actually nmap a different file.
You map one file into another?
The same virtual.
It will build content.
No, I have no idea, Zafang. So
Build content.
so essentially what you're saying is that,
Overlay one nmap.
yeah,
And
so,
the underlying is still remembers when you try to do unmap.
do you know the use case for why Do you know the use case? Why is it? useful?
You want to reserve like 4 gigabytes memory to load some as all. But then the actual file, the actual segments are for different.
Okay, just for everyone, what Javank is saying, which I mean, it's possible to guess, but I never ran into it. He says that it's possible to create one VMA and then like create a like kind of a subset of it, which is also a VMA, which sits in between and maps maybe a different file, for example. Or maybe one of them is even anonymous and one is a file, but I don't know how they.
Typically, like there's one of your.
Yes.
Serve.
No idea. Do you know how to go about it?
Don't have a guess.
No, like you see that you can like Javank says that the use case is to reserve a giant region of virtual memory upfront, so it's available to you, and then map individual maybe like parts of different files into this region for whatever reason. So maybe this functionality is supported. There is also something what is called irregular mappings, which I didn't want to explain, and I don't really know how they work, but it's a way where this the region which is backed by a file is not continuous, but with some gaps, and they're somehow arranged somehow. But I think even this is good enough to start to understand how it works. But yeah, if you have an answer, Javank, for how it works, tell us. Like we can discuss next time, but maybe it will take you days to figure it out. So I don't want to waste your time for this. I'm sure that there is a way to figure it out, to figure out the trick. Okay, so then I will stop. So I will take a picture of myself, and hopefully again I will assign a homework which asks you to like talk about it, and then hopefully we can publish it again on a class web page with all of your names attached to it. That's for the reason that if you ever say, look, your resume, I did it. So you guys, if you want to know what my education is about, I wrote parts of this blog post, which talks about virtual memory in Linux, and then hopefully it will increase your, what is it called? Competitiveness on the job market, but also for everyone else who comes after us. Instead of like digging through 2 books and multiple blog posts, they can maybe start with just ours and be happy. Okay, but that's coming later. And then I will also assign finally the lab, which will ask you to build the memory, like the body for xv6. It's an actual programming assignment. So you don't just write, you have to code as well. Okay, thank you.